Good afternoon, students. Okay, yesterday we have seen the topic about the quotient group. So, after quotient group, we have seen even the theorem also. The quotient group of a cyclic group is cyclic. Okay. Next, we have the concept of conjugacy and class equation. Okay, in this one small 5 marks question you will get, and even you have the chance of getting one 10 marks question. Okay. So, what is conjugacy and also class equation definitions are there in this? So if you'll see the conjugate element, okay, one element will be conjugate to another element. So the definition, if you see, it is let G be a group and A comma B belongs to G. A is said to be a conjugate of B in G if there exists an X belongs to G such that A is equals to XB X inverse. Okay. So whatever you have here, so this is the main definition of that is conjugate element. That is A is equals to X, B X inverse. A and B are the elements in group G. And even we are taking the X is the element from G. Okay. Then XB X inverse is called the conjugate of B relative to X. Okay. So if A is conjugate to B, then we write this is the symbolic representation of a conjugate elements to each other. Okay. That is A is conjugate to B. Okay. So this is the definition of the conjugate of a elements. So yeah, next we have the theorem we have, that is let G be a group, define a binary relation, that is conjugacy, on G by A conjugate to B if and only if A is conjugate of B in G. Then conjugacy is an equivalence relation on G and is called the conjugacy relation on G. Okay. So here we have the theorem is there. Okay. This theorem is not important. So just if you know the conjugative element, it's enough. Next we have conjugacy class we have. Okay. So this is the very important concept. That is let A be any element in G. Let A be any element in G and define this is class of A. C of A is there, no? It is called as class of A. It is equals to XA X inverse. Okay. So class of a conjugacy is defined as C of A is equals to XA X inverse such that X belongs to G. Okay. So this is important. Sometimes definition is asked. Okay. What is a class of conjugacy? So then C of A is the set of all conjugates of A in G and is called the conjugacy class of A in G. Okay. There we have for the conjugacy, we have the definition is A is equals to XB X inverse. Okay. A is equals to XB X inverse. Okay. And here we have for the conjugacy class, we have XA X inverse we have. Okay. So this is the definition of the conjugacy class. So after this, we have the theorem. So note that C of A is nothing but the equivalence class of the relation. Okay, what we have seen above, that is the equivalence relation is there on that one. Okay. So yeah, just 5.4.4 theorem. Whatever the statement are there, those are important, but the proof of the theorem is not important. Okay. Just here the theorem is that the G be any group, then the following hold. That is any two conjugacy classes are either disjoint or equal. Okay, this is important. For solving other theorems, this concept we'll use there. Okay. So any two conjugacy classes either. So if you take one class as C1, another class as C2, then whenever you take the intersection of those two, then you may get either disjoint or equal. Okay. And next one is the union of all the conjugacy classes is G. Okay. The union of all, if you write a C1 union, C2 union, like that, all the union of all the conjugacy classes, then those will be in G. Whatever the resultant you will get, those will be in G. Okay. Next, this is the theorem, small theorem we have. Sometimes it will be asked for 5 marks question. That is, let G be a finite group and C of A1, C of A2, C means up to n elements. Finite group in the sense it will have the n elements. So here we are taking class of element, that is conjugacy classes from A1 to AN. Be all the distinct conjugacy classes in G. Then mod of G is equals to summation I equals to 1 to N mod of, that is C of AI. We have to show this one. And with the help of that, G is a finite group. Okay. So the proof is we have C of AI intersection C of AJ. Before theorem, we have seen no 5.4.4 here. Just above we have. So I have told no the statements are important. So here when you are taking the conjugacy of two elements, they are disjoint. Okay. We know that either they are disjoint or equal. So here it is disjoint we have. So here C of AI intersection C of AJ is equals to pi for all I not equals to j. And next one is, that is a union of the conjugacy class. The union of all the conjugacy classes is G. So that's why here we are writing union of all the conjugacy classes equals to G. Okay. We are showing that G such that C of A1, C of A2 up till CF AN. Okay. Therefore, mod G, when you take the mod of this one, then you are writing whatever the elements are there, you are writing as a mod of C of A1, C of A2 up to C of AN. So that you can write in the shortcut as, that is summation we are taking. So here they are in the form of sum. So you are writing in the form of summation as summation I equals to 1 to N mod of C of AI. Okay. Here I is from 1 to N. So this is the important theorem. 5 marks you will get. Next, we have the definition of center of G. So center of G concept is also important. So on this, you center of G definition will be asked, and below 5.4.7 theorem will be also asked. Okay. So definition is, let G be a group, define the set Z of G. So representation here, C. C of A is conjugacy class. Z of G is called as a center. Okay. Z of G is equals to A belongs to such that AX equals to XA for all X belongs to G. Here it satisfies the abelian property, that is a commutative property satisfies. Okay. Whatever the conjugacy elements are there, if they satisfy the commutative property, then we call it as a center of G. Okay. Z of G is equals to, this is the main definition. A belongs to G such that AX equals to XA for all X belongs to G. Then Z of Z, the set of all self-conjugate elements of a group G is called the center of G. Okay. So we have seen what are the conjugate elements. So here we have one more point, that is a self-conjugate elements. Self-conjugate elements means whichever the elements are there, if they conjugate by themselves, they are called as the self-conjugate elements. So you can see the definition of that is self-conjugate elements. So self-conjugate elements means self-conjugate elements. Okay. Let A be an element of group G, and if conjugate class of A contains only one member, A belongs to J, then A is said to be a self-conjugate element. So we have seen the conjugate definition from that. If X inverse A X equals to B, if it is there, means it is a conjugate element. Okay. But if you have the in place of B, if you have A, okay, X inverse AX equals to A, then those elements are called as self-conjugate elements. Okay. So that is a definition of that. So center of G, this representation is important. Next, we have the theorem 5.4.7, that is the center. Okay. The center Z of G of any group G is normal subgroup. Okay. The center Z of G of any group is a normal subgroup. We have to show that. Okay. To show that it is a normal subgroup, first we have to show that whatever center is there Z of G, it is a first subgroup. Then we have to show that it is a normal subgroup. Okay. So whatever the Z of G definition we have seen, from that you can see that to show, first we need to show that it is a subgroup. So, so whatever the definition of a subgroup is there, in that we have seen three definitions are there. Okay. So in that we are taking one definition whenever G is an, that is a finite subgroup is there. There we have seen the definition, that is AB inverse belongs to H. Okay. So if A belongs to H, so we have seen this definition, A belongs to H, B belongs to H. Okay. A necessary and sufficient condition for a non-empty subset H of a group G to be a subgroup is that A belongs to H, B belongs to H, implies AB inverse belongs to H. Okay. This is the definition of the subgroup we have seen. So with the help of this, we are proving that here Z of G is a subgroup of G. Then we are showing that it is a normal subgroup. Okay. So here first let G be a group. Let G be a group, since E identity element we are taking, that is E into X is equals to whatever the identity property we have now, that we are writing here. E into X is equals to XE. For all X belongs to G, we have E belongs to, E is the identity element. E is the identity element which belongs to Z of G. So Z of G is non-empty. Z of G is non-empty means it has some element. So here we are taking the one element as the identity element. Okay. We shall prove that Z is a subgroup of G. Okay. To prove that, we are taking two elements, A comma B belongs to Z of Z, implies AX equals to XA. Okay. And BX is equals to XB. That is the commutative property we are telling. For all X belongs to G, for all X belongs to G by the definition of center. So what is the definition of the center? We have seen that it is the commutative property is there, no? AX is equals to XA. With the help of that, you are writing this. So AX equals to XA and X B inverse equals to B inverse X for all X belongs to G. Okay. So we are taking here B inverse and B inverse. So it has become that AX is equals to XA and XB inverse equals to B inverse X. So AB inverse of X is equals to A into B inverse X equals to A into commutative property we are using here, AX B inverse. Okay. So just if you interchange that, you will get this XA into B inverse equals to X into AB inverse. So AB inverse X is equals to what we got here, X into AB inverse for all X belongs to G. Okay. So here we got AB inverse, here also AB inverse. Okay. So for by this we can say that AB inverse belongs to Z of G. So that means Z of G is a subgroup of G. Okay, now we shall prove that Z of G is normal subgroup. So by the definition of the normal subgroup, we have to prove that it is Z of G center of class is a normal subgroup. So for that we are taking, let A belongs to Z of Z and Y belongs to G. Okay, Y belongs to group G and A is the element which belongs to Z of G. Then we have, that is a center definition is that YA is equals to AY. Commutative property, no? For all A belongs to Z of G and Y belongs to G. Okay, with the help of the property of center of G, we are writing it as, that is AY, YA is equals to AY. That is commutative property we are using. Next, so then YA, Y inverse equals to YA, Y inverse. Okay, YA, Y inverse you have taken outside. So A into, this is we are here we are doing the commutative property. Okay, so Y, for YA we are taking the Y inverse. Okay, when you multiply that, you are taking that is you are taking inside YA and Y inverse outside. So by commutative property, YA is equals to AY, no? So that's why A you are taking outside with the help of the associative property, and we are writing A into Y inverse. So what will happen? Y into Y inverse is E. Therefore, it is equals to A, belongs to Z of Z. Okay. Thus, Y belongs to G, A belongs to Z of G implies YA, Y inverse belongs to Z of Z. So we got YA, Y inverse value is equals to A, belongs to Z of G. So this is the definition of the normal subgroup. Okay, we have seen the definition. No? From that, we can say that hence Z of Z is a normal subgroup of G. Okay, so this is the important one. After that, okay. Next, we have theorem 5.4.9. This is the 10 marks question you will get here. This is the block 2, no? So 10A question or 10B question you will get from this one. Okay. Let G be a group and Z of G be its center. Suppose G by Z of G is a cyclic. Okay. Cyclic in the sense it generates the elements. Then prove that G is an abelian group. Okay. So here G is the group we have, Z of G be its center. Suppose if G divides Z of G is cyclic. Whenever it divides that one, it is cyclic. Then we have to prove that G is an abelian group. Okay. Suppose that G by Z of G is equals to X of X Z of G. So we are taking the element X from the group G. Then G by Z of G is equals to, that is whenever it is a cyclic means we'll write it in the form of A to the power of N. No? Okay. So A to the power of N is, we are taking here the element is Z into, sorry, X into Z of G. Okay. We'll write G is equals to, this is the for cyclic group, no? Okay. So that means whatever the X is there, the X is will be in the form of like this, X equals to A to the power of N. So here the element is this one, A. Instead of A, we have X into Z of G. So whenever you write in the form of like this is the X into Z of G to the power of N, such that N belongs to Z. Okay. So it is equals to, when you, that is X to the power of N, Z of G such that N belongs to Z, we are writing. To prove that G is abelian, so we have to prove that G is abelian. This is first part is that it is a cyclic. So we are defining that one. To prove that G is abelian, let Y comma Z belongs to G. Okay. So we are taking two elements from G such that then the element is in the form of, here the element is in the form of X into Z of Z, no? So the another element is Y into Z of Z. Third element is Z into Z of G. So these two belongs to G by Z of G. So hence Y into Z of G is equals to X to the power of N Z of G. So we got here, no? X to the power of N into Z of Z, this value. Okay. So Y into Z of G is equals to X to the power of Z of G, and hence Y into Z of G is equals to whatever is here is there, it is defined here. And even Z into Z of G also, we are writing in the form of X to the power of M Z of G for some integers N and M. So we are defining these from the above one. Okay. In particular, Y belongs to X to the power of N Z of G, and Z belongs to X to the power of M Z of G. Hence, so what is Y value here? We are taking the Y value as Y is equals to X to the power of N A and Z is equals to X to the power of MB for some A comma B belongs to Z of G. So we are taking the two elements such that it will be convenient for us to solve that it is an abelian. That is Y is X to the power of N. That is in place of Z, we are taking A. Z is equals to X to the power of M B for some A comma B belongs to Z of G. Now to show that it is abelian, we are multiplying Y into Z. So Y into Z, when you multiply this, you will get X to the power of N into A, X to the power of M into B. So you can do this one with the help of, that is X to the power of N you are taking outside, and B. So whatever this part is there, you are writing as A to the power of X to the power of M. By commutative property, this one, X to the power of M into A into B equals to, we know by logarithm properties, X to the power, A to the power of M into A to the power of N is equals to A to the power of M plus N. So through that property, we are writing it as X to the power of N plus N into AB. Okay. Now X to the power of M plus N, AB can be written as Bn, that it is a commutative. Therefore, BA, and it is equals to, you are splitting again this one. So X to the power of N, X to the power of N into B into A. So what you are getting, X to the power of M, again interchange of the, by commutative property, X to the power of N into B, X to the power of N, A. Okay. So again, if you take this one outside, X to the power of M into B, and this is X to the power of N into A. So this is Z and this is Y. Okay. Our intention is show that YZ is equals to ZY. That is, it is satisfying the commutative property. Therefore, G is abelian. Okay. Next, we have 5.4.10. So normalizer definition will be not asked, just if you know with the definition, then you can solve the, whatever the theorem is there, 5.4.11, there you can see. So let A be an element of a group G. Define the set N of A. C of A means conjugacy class. Z of G means center. N of A means normalizer. Okay, remember these terms. So define the set N of A is equals to X belongs to G such that AX equals to XA. Then NA is called the normalizer of A in G. Okay. So this is the definition of normalizer. So then A be an element of group G. Here we are taking element of G. Define the set. Here we are defining one set which is having the conjugacy elements. Conjugate elements, if you write in the form of one set, then we call it as a normalizer. AX equals to XA. So then N of A is called the normalizer of A in G. Okay. Next we have theorem. This is important theorem. Let G be a group and A belongs to G. Then the normalizer N of A is a subgroup of G. Okay. So we have to show that N of A is subgroup of G. Okay. So before, for center of group G, we have seen the theorem proof. No? Same similarly with the help of that, we are proving here. That is, since AE equals to A equals to EA, E belongs to N of A. Hence, N of A is non-empty. Okay, we are showing that N of A is non-empty set. Okay, suppose that X comma Y belongs to N of A, then X comma Y belongs to N of A. Okay, then X comma Y belongs to N of A implies AX equals to XA. That is a commutative property, and AY is equals to YA. Okay, these two with the help of the commutative properties. Therefore, xy into A is equals to X. If you take outside, we'll write YA equals to X AY. This is the commutative property again. AY equals to XA into Y. again ax into y is equals to a into xy. A into xy. So xy into a is equals to a into xy. We are showing that. Okay. Hence x comma y belongs to n of a. From ax equals to xi, it follows that x inverse a is equals to, it follows that x inverse a is equals to x inverse ax into x inverse. Okay. So it is equals to x inverse into xa. Here we are using again commutative property. X inverse xa x inverse. So what will happen? This is a into x inverse. So this inverse into x will become e. So what will be left? A into x inverse will be left. So that x inverse belongs to n of a. So whatever x inverse is there, it belongs to n of a. Thus, n of a is a subgroup of G. Okay. This is the another definition of subgroup we have. So for that we have taken A belongs to H, B belongs to H, AB inverse belongs to H. Okay. This is one of the definition of subgroup. So we have another definition of the subgroup. With the help of that, we are showing that n of a is subgroup of G. Okay. So next you can see the 5.4.2 12 theorem. Let G be a finite group. A belongs to G. C of A be the conjugacy class of A in G. Then mod of conjugacy class is, that is G, such that n of A, that is a normalizer, the index of n of A in G. Okay. So you can practice even this theorem. So next, this is the important one. 5.4.13. 5.4.30, this is the regularly asked question. Sometimes they will ask state and prove the class equation of a finite group G. Okay. Sometimes the statement will be given and you have to do the proof. Okay. So two types the question will be asked. Either statement will be given, proof you have to write, or else statement and proof both you have to write. Okay. So let G be a finite group, then mod G is equals to mod of Z of G plus summation I equals to 1 into M G, such that n of Bi, where Z of G is the center of G and B1, B2, B3 are M are elements of G, such that this is the class equation definition, such that C of B1, C of B2 up to Cm are the distinct conjugacy classes, each classes with more than one element. This equation is called the class equation of G. Okay. So just it has given like the definition of the class equation. So if statement almost this much length is there, no? So he will ask state and prove the class equation. So by the theorem 5.4.5, that is the conjugacy class we have, no? So there we have seen mod of G is equals to C of A1 plus C of A2 up to C of An, where C of A1, C of A2 are the distinct conjugacy classes in G. Among these conjugacy classes, some are with exactly one element, other are with more than one element. Okay. Whatever the classes are there here, in that they have some only one element and some they have more than one element. Also a conjugacy class C of A has exactly one element if and only if A belongs to Z of G, center of G. Okay. So by the definition of Z of Z, here we can see 5.4.8 theorem. So with the help of that theorem, we can say that thus the number of conjugacy classes C of AI, each with one element, is equals to Z of G. Okay. So here you are taking the elements in the class, conjugacy class, with only one element, you are writing them with equal to Z of J, mod of Z of G. Therefore, we can write mod G is equals to one element is we are writing Z of G plus summation I equals to 1 to M C of BA. Okay. So where C of B1, B2, Bn are all distinct conjugacy class, each more than one element. Okay. So here these are Z of G is with one element. Okay. These are the conjugacy classes with one element. And these are the conjugacy classes more than one element. More than one element. So you are combining them and writing like this. Okay. Mod G is equals to mod of Z of G plus summation I equals to 1 to M mod of C of Bi. Okay. Also by the theorem 5.4.12. What is the theorem? In page number 96 we have, that is a normalizer definition. On that we have theorem, no? Let G be a finite group, A belongs to G and C of A be the conjugacy class of A in G. Then mod of C of A is equals to G such that N of A, that is the G is the index of N of A. The index of N of A in G. Just now we have seen that one definition of normalizer. With the help of that you are writing C of BI is equals to G, that is the index of NBI in G. Okay. Thus we have, so here whatever it is there you include this one. This C of mod of C of BI is there, no? This is we are writing in place of that G such that N of BI. So here mod summation N equals to, sorry, I equals to 1 to M G, in place of this we are writing this one. Okay. So by the definition here we are using conjugacy class and also definition of normalizer we are using and class. So whatever the theorem we have proved with the help of the conjugacy class, through that only we are proving here this one. Okay. Okay. So this is the important theorem 5.4.13. So this is, if you see previous examination question papers, in that compulsory this question will be there. You can see there. Okay. So this 5.4.14, this is not important. And last one, 5.4.15 theorem. This is also sometimes, means not regularly, only sometimes it is asked in the examination. So you can go through this one. It is if P be a prime number and G be a group of order P square, then G is an abelian group. Okay. So if P is any prime number and G be a group of order P square, then G is abelian group. We have to show that. Okay, by this we are completing fifth unit. So after fifth unit, even I have told what are the important questions in this. So if you'll see 5.7, it is a model examination questions are there. So in the examination questions will be asked like this. First one, this is important. See. First one, that is define a normal subgroup of a group and prove that a subgroup N of a group G is normal if and only if every left coset of N in G is right coset of N in G. And even this one, this is the 5 marks one. Every subgroup of an abelian group is normal. Okay. Next, derive the class equation of a finite group. Just now we have seen, no, that one. So this is the rarely asked question. Sometimes only it will be asked, okay? Give an example of an non-abelian group in which every group subgroup is normal. So this is the important one, sixth one, 5 marks question. This is the with the definition he has given. If you check this one, this theorem will be that is the center of G is normal in G. We have to show. Okay. Explain the construction of a quotient group and give example. Every quotient group is abelian. This ninth one. Okay. And this. The quotient group of a cyclic group is cyclic. Okay. So in this almost this 11th, 9th, 7th, 6th question and 4th question. These are all 5 marks questions. And above one, even second one is also 5 marks question. First and third questions are the 10 marks questions. Okay. So after this, we have the most important unit in block 2. It is homomorphism. Homomorphisms and permutation groups. So in this only one more, that is the 10A question. Fifth unit, you will get the 10A question, and 10B question you will get from the 6th unit. That will be from the homomorphism. One question will be fundamental theorem of homomorphism of groups. Okay. So here we have first unit in the introduction, I have told about what is a function, mapping from one set to another set, what is a one-to-one function, and also on-to function, what is surjective function, what is injective function, what is bijective function. Okay. So those all concepts you will be have here. So in the introduction, you can see that here it is there. If G comma dot and this, if G comma dot and G dash comma star, here two sets are different. Okay. G is one set, here another set is G dash. Here is dot operation is there, here is star operation is there. Okay. So if you take two sets with different two operations and those are the groups, then a mapping from F G to G dash is called a homomorphism if F is compatible with the binary operations dot and star. Okay. Dot and star on G and G dash. To be more precise, for any A comma B belongs to G if A dot B equals to F of A star here. Okay. Two operations, two sets. Those two sets are, that is two groups we are taking. G is one group, G dash is another group. Okay. So here actual definition we have here. So this is the important one. Let G comma dot and G comma star be a groups. A mapping F G to G dash is called a homomorphism if F of A comma, that is F of A dot B equals to F of A star F of B for all A comma B belongs to G. Okay. This is the main important definition of homomorphism of groups. Okay. Here two symbols will be used, dot and star, and two groups will be there, that is G and G dash. Okay. So you have examples here. Let G and G dash be groups and define F mapping from G to G dash by F of X is equals to E dash for all X belongs to G, where E dash is the identity element. Okay. E dash is the identity element in group G dash. Then F is a homomorphism. Since F of AB, F of AB is equals to E dash, that is E dash into E dash. Here we are defining F of X is a function, E dash we are defining. f of x equals to e dash is the function we are defining. So when you are applying the definition of homomorphism, f of ab, here the product, just dot is there. Multiplication operation is there. Only one. So f of ab is equals to, through the definition, f of ab is equals to e dash. Okay. So you can write e dash as e dash into e dash. No, e dash into e dash is e dash only. So therefore, e dash is from the definition f of a and also from the definition f of b. Okay. So whenever f of ab can be written as f of a into f of b, the homomorphism is satisfied. Okay. Therefore, the given function is homomorphism. It is defining. Okay. For any group G, the identity map ID G to G defined by identity of is called the homomorphism. Okay. Here some examples are given. So which groups will be becoming the, that is, they are satisfying the condition of the homomorphism. So how many are there? 7 examples are there. You can go through them. So this is not important theorem. Next, these definitions are important. Okay. That is definition. Whenever a function G to G dash be a homomorphism, G to G dash be a homomorphism of groups, then F is called a monomorphism. Okay. We call it as a monomorphism if F is injective. Okay. Injective means here it is one-to-one function. One-to-one function. Okay. Epimorphism if F is surjective. Surjective means it is on to. Okay. Next, we call it as a isomorphism. This is very important. Okay. Isomorphism means F is bijective. That means bijective means 1, 1 and also onto. So whenever a function is 1, 1 and onto, we call it as that as isomorphism. Okay. Next, fourth one is an automorphism. If F is bijective and G and G dash are same groups. Okay. Here we have mapping from F G to G dash. Okay. But whenever F is mapping from G to G, that means itself. Within the group itself, if it is mapping, and if F is a bijective, then we call it as a automorphism. Okay. This, if you know the definition, easily you can do the theorems. So this is the important concept we have. Next most important one is, that is, what is the kernel of a homomorphism? Let F mapping from G to G dash be a homomorphism of groups. Then the kernel of F is defined to be the set. So kernel of F is defined as, this is the important. Okay, this is the important definition we have. Kernel of F is equals to A belongs to G such that F of A is equals to E dash. Okay. So A is the element which belongs to group G such that we are defining the function as f of A equals to E dash, where E dash is the identity element in G dash. Okay. Here you are taking the element A from G. Okay. Whatever the here E dash is there, it belongs to G dash. Okay. So here we are defining a relation between, that is, the two groups with the help of this, that is, kernel of F is equals to A is the element which belongs to G such that you are defining a function f of A is equals to E dash, where E dash is called the identity element in the G dash. Also, the image of F is defined to be the set. And this is also important. Image of F. Image of F is equals to F of A such that A belongs to G. Here F of A is defined as E dash. It is called kernel of F. If only we are defining F of A such that A belongs to G, then it is called as image of F. Okay. This is the important theorem. That is, let F mapping from G to G dash be a group homomorphism, then kernel of F is a normal subgroup of G and image of F is a subgroup of G dash. Okay. Kernel of F. Kernel of F is normal subgroup. Okay. Kernel of F is normal subgroup and image of F is a subgroup. Okay. The groups are also different here. Kernel of F is normal subgroup of group G and here image of F is a subgroup of G dash. Okay. These two we have to prove in the theorem. Okay. Now we are taking two identity elements. One element is E. It belongs to that is group G. E dash is the identity element in G dash respectively. Then we have kernel of F definition is we are writing here. That is kernel of F is equals to A belongs to G such that F of A is equals to E dash. Okay. Since F of E is equals to E dash, E belongs to kernel F and hence kernel F is a non-empty. Okay. Before theorems, if you remember, there we take the identity element and we show that whatever the given function is there, it is a non-empty subset of G. So for that, in place of A, we are taking E equals to E dash. So E belongs to kernel of F and hence curl F is a non-empty subset of G. Now, we have to prove it is a first thing. Whenever we are proving it is a normal subgroup, first we have to prove that it is a subgroup. Then we have to prove that it is normal subgroup. Okay. So for subgroup, what we have, A belongs to H, B belongs to H, AB inverse belongs to H. Okay. So you are taking two elements. A comma B belongs to curl F. So F of A is equals to E dash equals to F of B. Okay. F of A equals to E dash now. Therefore, we are taking F of B also equals to E dash. Then AB inverse belongs to H now. So F of AB inverse. So F of AB inverse is equals to, we are splitting this with the help of homomorphism. That is F of A into F of B whole inverse. Okay. So then in place of F of A, we are writing E dash. F of B, we are writing E dash. Okay. This is defined now. We are using E dash and E dash, but we have inverse. So E dash inverse equals to E dash. So E dash into E dash inverse means you will get the E dash only. So whenever you are getting the resultant as this one, so F of AB inverse also equals to E dash. This is from the definition, this one. Okay. Therefore, this whatever AB inverse is there, it also belongs to kernel of F. So therefore, AB inverse belongs to curl F. Thus, curl F is a subgroup of G. So it is satisfying the condition of the subgroup. Okay. Next thing is we have to show that it is a normal subgroup. Normal subgroup means XA, X inverse should belongs to curl F by the definition of normal subgroup. Okay. So also we are taking here, we need only one element for normal subgroup. So A belongs to curl F and X belongs to G. F of A equals to E dash. So this is from the starting definition and X belongs to G. Okay. So normal subgroup definition is F of XA X inverse. Okay. If you split this one, what will happen? F of X, F of A and F of X inverse. Okay. So here f of x, here you're writing here, but by the definition here, f of a value is e dash. Okay. So you're writing e dash, and f of x whole inverse we are writing. So it is equals to, here f of x is there, f of x inverse is there. Both will become the identity element, no? Just if you interchange this one. If you write e dash here, means what will happen? E dash into f of x whole inverse means you will get f of x whole inverse. So f of x into f of x inverse equals to, again you will get identity element e dash. So whenever you are getting identity element e dash, x inverse belongs to curl f. Okay. So therefore curl f is a normal subgroup of G. So compulsory you should know the definition of subgroup and also normal subgroup. Then only you can prove these theorems. Okay. And second part is that you have to show that image of F is equals to F of A such that A belongs to J. This is the definition of image of F. You have to show that it is a subgroup. Subgroup means what we have to show? AB inverse belongs to image of F. Okay. So through this definition, we say that since G is non-empty, image of F is a non-empty subset of G dash. Okay. Now you are taking two elements, that is x comma y belongs to image of F. You are defining x equals to F of A and y is equals to F of B. For some A comma B belongs to G. So we have to show that xy inverse belongs to image of F. So we are writing xy inverse. So what is xy inverse? X value is F of A. Y inverse is F of B whole inverse. Okay. So if you write like this, F of A, even inside also you can put the inverse. So F of A into F of B inverse equals to. So when you do the product of these two, you will get it as F of AB inverse. Okay. And this AB inverse belongs to G. Okay. So AB inverse belongs to G means it is satisfying the condition of subgroup. So implies XY inverse also belongs to image of F. Thus, image of F is a subgroup of G dash. Okay. So with the help of the subgroup and normal subgroup, like this you can prove the theorem. This is one important theorem. Next we have this theorem will be asked for 5 marks question. Here we have let F is mapping from G to G dash be a homomorphism of groups. Then F is a monomorphism if and only if curl F equals to identity element E. Okay. So we have to show that this F monomorphism of groups, we are defining that F is monomorphism. That is, it is satisfying the condition of 1 1 function if and only if curl F is equals to E. Okay. Mono means what? 1 1 will be there. So we are defining this one. Let F be a monomorphism. Then we are taking one element A belongs to curl F such that is F of A is equals to E dash. This is by the definition of the curl we have no. That is F of A is equals to E dash is equals to F of E. Okay. So that means these two are equal. So A is equals to E is here. Hence curl F is equals to E. That is a singleton identity element. So converse. So if and only if it is given, no? What is the question? Let F G to G dash be a homomorphism of groups. First thing we are showing that G to G dash be a homomorphism of groups. Then F is a monomorphism. Okay. Then F is a monomorphism if and only if curl F equals to E. So we are taking here F is monomorphism. Monomorphism is 1 to 1. We are showing that curl F equals to E. Okay. So here we are we are taking F is equals to monomorphism. Monomorphism means one-to-one function. So by the one-to-one function, we are defining that curl F is equals to E. Okay. Next, by taking curl F equals to E, you have to show that F is monomorphism. Okay. Converse means what? First part to second part and second part to first part. So conversely, if F is equals to E, then for any A comma B belongs to G, monomorphism means we have to show that the two elements, each and element, we have the definition of f of x1 equals to f of x2, then x1 equals to x2. That is the definition of the one-to-one function. Okay. F of A is equals to f of B implies f of AB inverse equals to f of A, f of B whole inverse. Okay. Implies f of A. In place of f of B, we are writing it as y because here A equals to E, no? So f of A into f of B whole inverse. So in place of B, we are substituting A. So f of A into f of A inverse is equals to E dash. So implies f of, that is AB inverse belongs to curl F equals to identity element E. Implies AB inverse equals to E. Implies A is equals to B means you are taking this B this side. So you will get A is equals to B. Hence F is an injection and F is a homomorphism. So we are showing that it is the one-to-one, it is satisfying the one-to-one function. Therefore, it is an injection. If it is an injection means if it is a monomorphism. Okay. So tomorrow we'll see the main important one, that is the fundamental theorem of homomorphism. This is the very important theorem. So it will be asked for 10 marks question, that is the state and prove the fundamental theorem of homomorphism of groups will be there. So in this only 2 more theorems are there. We'll see them and we'll conclude the block 2 here, and we'll see about the just the definition of the rings. Okay.